everyone, thank you so much for joining us today. My name is Anya and I'm a part of business development team at K-Mine. And before we start, as usual, I just want to remind you to please follow our LinkedIn page. It's the best way to stay connected with our latest events and webinars and updates. So today we're focusing on the resource assessment and profitability of heavy mineral deposits. We'll explore practical strategies for evaluating heavy mineral sands project, from conducting thorough geological assessment to determining economic viability, with an emphasis on optimizing both operational and financial outcomes. Before we begin, let me just briefly introduce you to K-Mine. The company was established in 1994 in Ukraine, and we expanded since then to Europe, United States, Canada, and our team is a strong blend of software developers, geologists, mining engineers. Some of them are certified under CRISCO compliant reports, so we have qualified persons that can provide an F43 101 and JORC standards. We support a very diverse client base, from early stage exploration teams to major mining companies, providing reliable and cost-effective solutions tailored to the unique requirements of each project. So let me just give you a little overview of what we do at K-Mine. Our bread and butter is software for mining industry. We support the entire cycle from exploration to production, and our platform offers flexible modules both for open pit and for underground operations. One of our key strengths is the adaptability of our models. So you can begin, let's say, with one model and then implement the full suite. It really depends on your project needs. With our tools, you can efficiently manage geological data, design optimized mining plans for both short-term and long-term projects. And additionally, through optional IoT and dispatch system integration, we enable real-time monitoring to ensure operations remain efficient and well-coordinated. But at K-Mine, our software is driven by real industry experience and developed to address the challenges that we encountered through our consultancy work. So as I mentioned earlier, our team includes qualified persons that can prepare technical report in compliance with NI 43-101, SK 1300, and JORC standards. These reports are customized for project stages like profitability, feasibility study, mineral resource estimation, and others. We bring extensive expertise across a wide range of harder commodities with particular emphasis on critical minerals. So if you'd like to learn more about how we can support your project, please leave a comment below or connect with us through our contact form on our website. So what are we talking about today? Today we'll walk through the fundamentals of heavy mineral projects. We start with the main ore body types and how to define geological domains, and then we'll look at the difference between total heavy mineral and valuable heavy mineral to understand where the real value lies. We'll also touch on optimizing cut-off grades, methods for grade interpolation, and how to balance heavy mineral grades with the overburden to mineralization ratio. And finally, we'll wrap up with the recovery feasibility, both for heavy minerals and associated byproducts. So when we look at global titanium mineral reserves, the data may vary depending on the source, but one fact always stands out. Australia and China consistently remain the leaders. And what's also fascinating is where titanium dioxide is actually found. Only about 30% comes from traditional sedimentary deposits we usually think of, like placers or paleoplacers. The majority, more than half, about like 54%, is contained in magmatic deposits, with the smaller amounts in metamorphic deposits, just around 1%, and lateritic deposits at about 14%. Even so, placer deposits still remain the most important and most profitable source of titanium, at least in the short to medium term. When it comes to titanium, the two most important sources are ilmenite and rutile. South Africa and Australia are the leading producers of ilmenite, while Australia also dominates rutile mining, holding an impressive 62% of the global market share. Other significant ilmenite resources can be found in countries like Canada, India, and Ukraine, which also play an important role in the global supply chain. The sediments that reach the coast contain varying amount of heavy and dense minerals, and over time, natural forces like waves, longshore currents, wind, and tides act as sorting mechanisms, gradually concentrating these heavy minerals into distinct layers. The end result is the formation of heavy mineral-rich deposits, laminated or lens-shaped bodies that can reach several meters in thickness and, in some cases, even extend to tens of meters. The geology that hosts mineralization is often stratified and may be clearly defined by geological boundaries or domains. As with any geological interpretation, it's important to understand not only when mineralization was deposited, but also the processes that came afterward. So in some cases, older shorelines may have been eroded and then overlain by younger ones, which with different mineralogy depending on the sediment sources. And in other situations, shoreline mineralization could have been reworked into dune system. We also see weathering horizons linked to oxidation reduction fronts or sediment brought in by rivers and later reshaped by erosion. Over time, deposits may undergo compaction and consolidation, and in certain environments, sulfide horizons or acid sulfide soils can also develop. To illustrate, an updated stratigraphic framework for a region can completely reshape our understanding of paleoreconstructions. And since these reconstructions form the basis for predictive studies and exploration, such changes can have a major impact on how we assess and search for new deposits. When assessing resources, it's not enough to simply look at the overall deposits. We also need to consider the distribution and association of heavy minerals, the boundaries between different sedimentary phases, grain size characteristics, base of mineralization, secondary changes such as like weathering and the presence of clay layers, rock fragments, quartz aggregates, and sulfides. Defining mineralogical domains is critical for accurately representing mineral resources in the subsurface. Depending on the nature of the deposit, interpretation may involve a mix of closed wireframes and surface models, which are then used to code these domains into the block model. Equally important that these domains would be identified with enough representative mineralogical samples so that material from different domains isn't unintentionally combined in a single composite. We also need to pay close attention to the lab methods used when evaluating heavy mineral content in sands. Sometimes, in order to save on the cost of thousands of mineralogical analysis, routine samples are only tested for concentrate yield, measured in kilogram per ton after separation in heavy liquids. And that yield is then used as a basis for defining composite samples. But according to research by Jones, Gibson, and O'Brien, the cost of a composite mineral assemblage analysis can vary widely from about $400 to as much as $2,000. So the price depends on the method is used, whether it's purely chemical analysis like ChemScan, or a combination of physical gravimetric separation with chemical testing such as magnetic and electrostatic separation, and sometimes combined with heavy liquid separation techniques like Clarici or TMF, followed by X-ray fluorescence analysis. So let's take a closer look at how composite mineralogy samples are formed. It begins with a raw sand sample, which is first washed, then dried in an electric furnace and weighted. From the dried material, a portion is selected by quartering, weighted again, and then separated in heavy liquids until all of the light fraction minerals are removed. The heavy mineral concentrate is then carefully washed, dried once more, and weighted. This process allows us to calculate the yield of heavy mineral concentrate per ton of rock. Essentially, we take the weight of the dried residue in grams, multiply it by the weight of the resulting concentrate, and then divide it by both the weight of the original sand sample in kilograms and the weight of the portion taken after quartering. Based on the concentrate yield, routine drill hole samples are grouped into composites like barren material, low grade, medium grade, and high grade. Samples with barren or low mineral content are not analyzed further, and the remaining samples with similar concentrate yields are combined into group composites. These group composites are then processed further by separating them into electromagnetic or non-electromagnetic fractions, and each fraction is weighted and analyzed mineralogically. The percentage of individual minerals within the fractions is determined by counting grains, taking into account both their size and specific gravity. So it's important to remember that mineralogical assessment is not the same as metallurgical assessment. So mineralogical assessment focuses on identifying the types of minerals present, their grain size, their chemical composition. Metallurgical assessment, on the other hand, is more about testing how efficiently the minerals can be recovered and separated using different processing methods, and it's about understanding the qualities of the final product. To determine the chemical composition of minerals like rutile, ilmenite, zircon, specialists isolate monomineral fractions. These fractions usually contain between 95 and 99.5% of target mineral. On this slide, you can see the common minerals to make up a typical heavy mineral association, and another key point is quality control. It's essential to monitor blind samples and laboratory standards during the actual analysis rather than just waiting until data preparation. This way, any issues in the lab can be identified and corrected immediately, preventing errors from affecting the final assessment. This monitoring also includes making sure that correct frequency of standards and the blind samples maintained. And finally, duplicate sample analysis helps us understand the nature of sampling and analytical errors. It's also interesting to note that in countries of the former Soviet bloc, there is still a practice of reporting ore mineral content in kilograms per cubic meter using polygonal methods for resource estimation. So when content is expressed in kilograms per cubic meter, the determination of the bulk density of sand becomes critical. This directly affects the tonnage of ore sands and the conversion of mineral content from percentages into kilogram per cubic meter. For example, in many resource reports, the cutoff grade for outlining an ore body along drill holes might show ilmenite content ranging from 15 to 40 kilograms per cubic meter in alluvial deposits and from 20 to 50 kilograms per cubic meter in alluvial deposits. There is also usually a minimum thickness requirement for the ore horizon, often no less than 2 meters. The only exception is in rare drill holes where very high grades compensate for a thickness of less than 2 meters. Once the roof and the floor of the ore layer are outlined in each drill hole, the next step is to delineate the calculation block in plain view. For each drill hole, the average grade and thickness are calculated, and then within each block, averages across drill holes are determined. By multiplying these averages by the block surface area, the block volume is established. The ilmenite reserves in that block are then calculated by multiplying the sand volume by the weighted average mineral content. Finally, titanium dioxide content is calculated for each block. Each block is also subject to a limit, a minimum economic or cutoff ilmenite grade. This is usually expressed through an equation that takes into account not only the grade itself, but also the stripping ratio, meaning the volume of overburden compared to the ore horizon within the block. To calculate this, we first determine the minimum break-even ilmenite grade where there is no overburden, so when K equals 0. This considers the mining and processing cost at K equals 0, the market price of 1 kilogram of ilmenite, recovery rates, and the mineral content of the ore. For example, this value might be 42 kilograms per cubic meter. Then we calculate the break-even grade when the stripping ratio is equal to 1, which increases mining and processing costs. In this case, it could be 44.6 kilograms per cubic meter. And the difference between these two numbers, 44.6 minus 42, gives us 2.6 kilograms per cubic meter. That means that the minimum economic ilmenite content in a block can be expressed with the equation 42 plus 2.6 multiplied by K, measured in kilograms per cubic meter, where K is the stripping ratio. So when working with a block model, one of the most important parameters is the concentration of total heavy minerals, or THM. In most deposits, the minimum economic cutoff for total heavy minerals is around 1% or higher. To calculate the content of valuable heavy minerals, or VHM, from total heavy minerals, we need to know the percentage of specific minerals within the heavy mineral fraction, things like ilmenite, rutile, zircon, and others. But here's the challenge. Using total heavy minerals as a cutoff grade factor for resource reporting can sometimes be misleading. In certain areas of a deposit, the mineral mix may actually be more valuable because of a higher percentage of zircon, which is generally worth more than titanium-bearing minerals. That means applying a cutoff of 2 or 3% total heavy minerals could underestimate the true potential of the resource. To find the most appropriate cutoff grade based on heavy mineral content, a preliminary optimization of the resource model is often required. So one of the biggest challenges in the resource estimation for mineral sands is getting an accurate breakdown of minerals like ilmenite, rutile, zircon, leucoxene, because the production cost can vary dramatically depending on which mineral dominates. Ilmenite is usually the most abundant titanium mineral in heavy mineral sand deposits. Its theoretical titanium dioxide content is about 53%, but interlayering and weathering can change this significantly. In fact, after deposition, weathering often enriches ilmenite by leaching out iron, which naturally upgrades its titanium dioxide content. By contrast, rutile contains about 95% titanium dioxide, but typically it's less abundant than ilmenite in most deposits. That means weathered or altered ilmenite can have a very different market value compared to unweathered primary ilmenite. Ideally, mineral sands should be treated as polymetallic deposits with valuable heavy minerals converted into a common equivalent. One approach is to express resource value in dollar terms per ton by multiplying the value of each mineral concentrate by its tonnage in the resource model. This methodology makes it possible to refine the cutoff grade more accurately, especially when the proportions of valuable minerals vary significantly across the deposit. It's somewhat similar to how metal equivalency is calculated in polymetallic ore deposits, leading to what we might call a resource indexing code. The formula works by summing the product of conversion factors and the contents of each mineral. These conversion factors are based on both the recovery rate and the relative market value of each mineral. For example, let's say ilmenite is the main mineral, but we also recover zircon, rutile, kyanite, starolite, and first we determine the value of 1 kilogram of each mineral in concentrate, essentially the price of the concentrate divided by the mineral's content per ton. Then we calculate the price ratio of each mineral compared to ilmenite. For instance, rutile may be worth 5 times more per kilogram than ilmenite. Then we factor in the recovery rate for each mineral compared to ilmenite. So by multiplying these ratios of price, recovery, we obtain conversion coefficients that translate all mineral contents into ilmenite equivalent. For example, zircon might have a coefficient of 5.9, rutile is 3.6, and so on. So these coefficients are then applied into the formula to standardize resource estimates. When evaluating a project, the depth of the ore horizon can be accounted for using a coefficient. This coefficient is calculated by dividing the average heavy mineral content for an interval by ratio of overburden thickness to the vertical thickness of the mineralization. So this method can be applied both to individual drill holes and to resource models. Earlier, we looked at an example of this polygonal estimation where the stripping ratio was considered for a block. The difference being that in that case, volume was used rather than thickness. And the benefit of this approach is that it highlights areas of the deposit where the value of the ore outweighs the cost of removing the overburden. In resource evaluation within the countries of the former Soviet bloc, for example, such areas often will be excluded from calculation of economic reserves and instead will be classified as sub-economic. These zones may become viable in the future if economic conditions improve or, for example, if new technology emerges. And this principle really aligns with the JORC reporting guidelines, which require that reported resources must have reasonable prospect for eventual economic extraction. Ultimately, the choice of an appropriate cut-off grade depends on the mining parameters planned for the deposit, as well as the professional judgment of the competent persons that conduct the resource estimation and the resource assessment. Based on the studies of different ore body types and heavy mineral assemblages, the threshold range of about 0.5 to 1 is generally sufficient to define mineralization with reasonable prospects for economic extraction. When it comes to interpolating grades within a block model, heavy mineral sands are most often evaluated using methods like inverse distance weighting or nearest neighbor interpolation, and in both cases, only samples from the relevant geological domain are used. Sometimes kriging is applied as well. In that case, the geometry of the ore body, grade anisotropy, the density of the drilling grid, and the chosen block sizes all become very important factors. As a rule of thumb, drill spacing of about 60 by 60 meters, 100 by 25, or 50 by 20 meters usually corresponds to the measured resource category. Spacing closer to 120 by 120 or 250 by 50 meters generally falls into the indicated category, while grids of 400 by 50 meters or wider are typically classified as inferred. Still, it's worth remembering that drill density and anisotropy ellipsoid parameters are really just measured of sample spacing and the directional variability of the deposit. When defining resource categories, it's also important to look at statistical measures, for example, the effectiveness of kriging. If ordinary kriging is used as the main estimator for total heavy minerals and valuable heavy minerals values, the slope of regression can help guide classification. When the slope is greater than 0.85 and other requirements for classification are met, the source can be considered measured. Where the slope falls between 0.7 and 0.85, even if other criteria suggest a high category, the resource should be classified as indicated. And when the slope is less than 0.7, the resource is classified as inferred, regardless of whether other criteria point to a high category. So when it comes to mineral resource reporting, the JORC code and other reporting codes provide guidelines on how to present the most significant figures. For tonnage of material or resources and reserves, it's recommended to round to two significant figures. For example, 5,103,456 tons could be reported as 5.1 million tons. For heavy minerals, tonnages can be also rounded to two significant figures. So 11,333 tons would be reported as just 11,000 tons or simply 11 kilotons. And percentages of heavy minerals should generally be reported to three significant figures when they are above 10%, and to two significant figures that they are below 10%. For example, 10.1% heavy minerals or 9.8% heavy minerals. For mineral associations, it's recommended to round to the nearest whole number, such as, for example, 57% ilmenite. And for clay percentages or oversized material percentage, these should be also rounded to the nearest whole number. So, as I already mentioned, mineral sand deposits are often complex. For example, at one of the largest deposits, in addition to zircon, rutile, and ilmenite, production also includes kyanite, stillimonite, and starlite concentrate. Among the byproducts, there are also valuable elements such as tantalum pentoxide, niobium, vanadium, scandium oxide, hafnium, and more recently, the researchers have been investigated the potential for gallium and germanium to be present in mineral sands where they can be economically extracted. Meanwhile, demand for titanium dioxide minerals continues to rise, particularly in light of ongoing geopolitical conflicts around the world. Many mineral sand deposits also contain monazite and xenotime, which are important sources of rare earth elements. These are the same elements that are used in smartphones, computers, and medical devices. And as the world moves towards a low-carbon economy, the demand for rare earth is only increasing, since they are essential for making hybrid cars, electrical vehicles, and wind turbines. When it comes to titanium, most of it isn't consumed in its metal form, but as a titanium dioxide. In powder form, titanium dioxide is a brilliant white pigment used in paints, paper, and plastic. It's valued for its brightness, whiteness, very high refractive index, and strong opacity. Titanium metal, on the other hand, derived from rutile, ilmenite, or leucoxene, finds its way into high-tech and high-performance applications, everything from spacecraft and guided missiles to jewelry, artificial joints, and even heart pacemakers. According to the International Titanium Association, global demand for titanium dioxide is expected to grow by about 5% annually through 2030, fueled by rapid urbanization and industrial growth. Zircon demand is also rising sharply, driven by its key role in ceramics and refractories, with the growth linked to the construction and automobile industry. And at the same time, the steady need for high-performance material in aerospace and electronics continues to support demand for mineral sands. The transition to cleaner energy is another important driver. Minerals like ilmenite, which is used in solar panels and renewable technologies, are becoming increasingly critical. In fact, the International Renewable Energy Agency projects that the renewable energy sector will grow by 50% between 2022 and 2030, which will further push the need for minerals sourced from minerals and deposits. So these trends are shaping global market dynamics, driving both investment and exploration, particularly in resource-rich regions. That's why over the next 5 to 10 years, advancing methods of exploration and sampling, improving 3D modeling of minerals and deposits, applying geostatistical techniques for resource evaluation, and developing geometallurgy or other mineral studies will be priority areas for the industry. And as far as K-Mine, we provide both software solutions and consulting services for mineral resource evaluation and mine planning, including projects focused on mineral sands. For more than 10 years, we've been working successfully with leading titanium producers in Eastern Europe on the extraction of zircon, rutile, ilmenite, kyanite, starlite, and sillimanite. And among our partners are well-known companies such as Velta, Group DF, and UMCC Titanium. So I think that's it for today. Thank you so much for joining us, and I'll see you next time.